Am I snazzy yet? Suppose for a moment that our understanding of physics, specifically magnetism, is lost. We would still have a compass. We would still have fun playing with a containment, and that's a bit pretentious, I know. We would lose the fun of playing with a magnet like a scientist. And that is why I'm grateful. Science helps us in our day-to-day lives, but we rarely notice them. As a modern citizen, it is my duty to embrace science. Not to forget religion. It's a big part of our lives, but science is also a factor. I'm not making a statement here. I'm not. That's not why I'm here. I'm here to talk about physics, because I love it. It's simple. This here is a compass. It points towards the Earth's magnetic north. It is fun. I still play with it, being as I am snazzy. Since ancient times, people have used it more productively, let's say. They were snazzy too, because they were scientists. But they used it to discover untrodden lands. I'm talking about navigators. They used it to explore the ideas of magnetism. I'm looking at Michael Faraday. But where does the Earth get its magnetism? It's not a magnet. It's more like a dynamo. And the basic principle is a movement of charges create a magnetic field. But where do we have charges and where do we have movement? To answer this, let's dive right down into the Earth's inner layers. This is the Earth's outer core. And it is here where the magnetism is generated. The Earth's outer core is made of nickel and iron. And due to the immense heat from the inside of the Earth, they melt. And molten fluids have something called convection currents, like so. So when you have a hot base and a cooler upper region, you have a movement of heat that goes up because hot fluids are less dense than cold fluids. The cold fluids from the upper region move down, heat up, and they move back again, and this is called convection currents. But in the spherical Earth, something different happens. You may have fields or columns of heat, as I like to call them, going this way, or maybe this way, or maybe this way. Oops. Okay, we have one of them. It's a random distribution, kind of. So we won't have like a north-south orientation of the magnetism like we see in the Earth. Instead, we have broken these on the floor. But we need to take into account the Earth's rotation. Due to the Earth's rotation, we have something called the Coriolis Effect. And it is an effect which regulates the flow of the current and make them move in north-south orientation, and thereby we get a regular movement of current. Where do we get charge? Well, let's dive right down into the atoms. This is an atom. It's a nucleus being orbited by electrons. Now when we heat up an atom, the outer electrons escape. And when they do, since they're negatively charged, we have basically a charged field. And due to the Earth's movement, due to the movement of the current, we get a movement of charges, and thereby we get a magnetic field. But why should we care, you may ask? In 1989, a huge solar flare disrupted the Earth's magnetic field, disrupted the Earth's atmosphere hugely. This is a solar flare, and it is dangerous, let me tell you. What happens is the sun's atoms lose all their electrons and therefore become positively charged, since we just have a nucleus. This is called plasma. Now plasma follows the curves of the sun's magnetic field. The field line, but the magnetism on the sun is irregular because it's a star and it's made of gas. So you may have two field lines that collide, and when they do, you get a huge spurt of plasma. The effects of plasma on Earth are beautiful. You get something like this. You may not see these from Arizona because the Earth's magnetism deflects them. But we do see them in the polar skies. What happens is, in the poles, the magnetic fields of the Earth converge, and these particles can hit the atmosphere, and since they're so energetic, they light up brilliantly in bands of light known as auroras. What happened in 1989 was just a solar fart. It wasn't really that big. What could happen was what happened in 1859. A huge solar flare caused auroras all over the Earth. People in Britain, miners, woke up in the middle of the night because they thought it was the sun. Telegraph poles spewed sparks, and operators were electrically shocked. If something like that happened today, forget a blackout, forget anything of the sorts that happened in 1989. Worldwide communication would be lost. How? How would we lose worldwide communication? Well, riddle me this. What gives us GPS, telephone communication, and the internet? And the answer is satellites. I like satellites. Explaining them are fun. So let's dive right into satellites. I'm going to be talking about the GPS satellites. The GPS satellites need impeccable timing systems, roughly 20 to 30 nanoseconds of error each day. What is a nanosecond? It's not a thousandth of a second. It's not a millionth. It's a billionth of a second. I would be right if I call it a fraction of a second, but that would be quite a euphemism. And we need to take into account the theory of relativity. It was a theory formulated by Einstein. It's what made him the great scientist in our mind. The theory of relativity states that the faster an object moves, the slower it measures time. GPS satellites are moving at 14,000 kilometers per second. That is very, very fast. Faster than your car. And so they measure time a bit slower than our wristwatches. But another principle of relativity states that the farther away an object is from a heavy mass, the faster it measures time. So, since the satellites are 20,000 kilometers above sea level, they seem to tick a bit faster. These two effects add up to give an overall error of 38 microseconds. That is 38,000 nanoseconds. And we need to tone this down to about 20 to 30. How do we do that? Well, the theory of relativity, the relativistic corrections, help us navigate ourselves and pinpoint you to the nearest 5 to 10 meters. Without these corrections, the GPS satellites would be lost, absolutely lost. They would measure an error of over 10 kilometers every day. Ladies and gentlemen, in my closing thought, I wish to point out that science is a beautiful thing. That science is more like an adventure of our mind and our reason than anything else. is the vast outreach of her imagination. Ladies and gentlemen, I'm still a teenager. So I made a GIF for you. And this to me is something to geek out about. But this to me is also something marvelous, something beautiful, something to see and feel. Maybe you could write a poem about this, and that won't be science. That would be the human heart. And this touches my heart as much as it touches my brain. Thank you.